Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at the method of successive over-relaxation. So in this topic, we will describe the concept of over-relaxation. We'll actually introduce it using Newton's method. We will then apply this concept to the gauss-zeitel algorithm, and we will consider any changes necessary to the implementation. All right, suppose that we are converging on not a single root, but a double root using Newton's method. Now, generally, engineers tend to avoid double roots since they tend to be unstable. However, just for argument's sake, suppose we have one approximation of the root. We find the tangent line, we find the root of that tangent line, and that is our next approximation. We evaluate the function at that point, find the tangent line, find the root of it, and that is our next approximation, and so on and so forth. What you're going to find is that the rate of convergence actually slows down. It now becomes order h and not order h squared. So this is going to cause a problem because we have a double root. The convergence is slowing. The problem here is that the numerator is going to zero faster than the denominator. So even though we have a zero, so what happens is each successive step is going to get smaller and smaller. So this is going to slow the rate of convergence, something we'd like to avoid. Now, suppose that we've calculated xk plus 1 given the value xk. So we are moving from one approximation point to the next. The question is, can we move a little bit more in the direction that we are moving towards the root? So for example, rather than just moving from xk to xk plus 1, can we go, say, 50% further? So more generally, given xk, can we move omega times the difference from xk plus 1 minus xk in the direction of xk plus 1? Well, we can. And so what we do is we're going to calculate x sub k plus 1, but having calculated x sub k plus 1, we will then set x sub k plus 1 to be x sub k plus omega times that difference. So for example, in the example below, omega would be approximately 1.5. If you just wanted to go from xk to xk plus 1 in one step, omega would be equal to 1. This expression can be simplified to just be 1 minus omega times the previous approximation plus omega times the next approximation. This technique is called over-relaxation, and if we continually do that every single step, we call it successive over-relaxation. All right, so thus, having calculated the next point, x sub k plus 1, by whatever algorithm you're using, if you choose a value of omega between 0 and 1, then this over-relaxation does not move as far as x sub k plus 1 originally did. This may be useful if you are overshooting the target and bouncing back and forth towards what you are trying to converge towards. If you just let omega equal to 1, then you have your original algorithm back. Your next approximation simply is x sub k plus 1. If, however, you choose a value of omega greater than 1, then this over-relaxation technique moves you further in the direction of x sub k plus 1. Now, If omega is too large, you're almost certain to overshoot the target. For Newton's method, and if you are trying to converge on a double root, it happens that omega equaling 2 is the ideal choice. So in this case, for Newton's method, rather than having the next approximation be x sub k minus that ratio of the function and its derivative, you instead use x sub k minus twice that ratio. Now, we didn't discuss that too much, or we didn't discuss it at all during the topic on Newton's method, because this doesn't come up too often in engineering practice. Double roots tend to be a finicky object because a small change can change a double root into two separate roots, or no root at all, indicating complex roots. Now, we can modify the gauss-zeitel method to include this additional push. Now, the ideal size of omega depends on the matrix, and you can look that up to find out exactly what it is depending on the eigenvalues. However, it's reasonable to start with values slightly larger than 1, say 1.1 or 1.2. Now, suppose we have the previous value for the ith value or ith entry of our approximation of the solution. So u sub k I, and then we find the next approximation, which with Gauss-Zeitel is found with this algorithm. In that case, we would find that next value, but then update that next value with this linear combination of the previous value and our next calculated value. And note that 1 minus omega plus omega is equal to 1, so this is in fact a linear combination. It's in fact a weighted average. So here's our implementation. What's changed? Well, actually only one line of code. This one line of code used to be simply setting the ith entry of the vector u to be the previous value divided by the diagonal entry. So we change it slightly. Now we are taking 1 minus omega times the previous value plus omega times that value we calculated. That's it. And if omega is small, say 1.1 or so, it can reduce the number of iterations required. Following this topic, you now understand the idea behind over-relaxation. And doing this over and over again is successive over-relaxation. You're aware that this is a push in the direction of the next approximation we find. You understand that the ideal value of omega, at least for Gauss-Zeitel, depends on the matrix. But it's reasonable to start with something like omega equaling 1.1. You understand that this can speed up convergence, but it can also slow it down. This, of course, makes it useful for simulations where you are using the matrix over and over again, and thus you can tweak the value of omega. You are aware that this is also a trivial change in code. This only requires order 1 additional operations per entry of the vector, or order n additional operations per step, which is actually not that much, given that if the matrix is dense, there's n squared operations still involved. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!